But let me begin with there are a few things. I'll do three things, right? This one is distributed form, and then the exponents. Let's start with comparison. So you remember how to compare two numbers, huh? So you say, 137, we say less than 181. The meaning of this is that you start with 137, you count a certain number of steps, and you land at 181. Or if you like, start at 181, you count backwards certain number of steps, and you land at 137, right? So that's how we compare. Now, so I actually glad I forgot who it was Wednesday, I guess. I think somebody else reminded me. I thought I need a precise definition of less than for mathematical reasons. And Wendy was saying that for little kids actually that's useful. Oh, it's good to know that what you want to do turns out to be useful for other people, right? And so, but for mathematical reasons, we need definition. Yeah, so, by the way, so, what was your impression of definitions? Do you think it was something that somebody's crazy insistence but means nothing instead? Do you people get the impression in the school culture, in the usual school culture? Well, I don't want people who have gone through this institute to answer, obviously. The experience I had with teachers was, I won't go through the whole story, but what was blotted up at the end was, what do you want? Oh, no, I said, you really need definition or something. And he said, what do you want? One more thing for my kids to memorize? That was the general reaction, pretty much. But as I said, this is part of what we try to correct, that the school mathematics culture has degenerated to the point, for reasons that we never taught you, not you, I mean, we never, universities and colleges never teach anything useful. That's the origin of the whole problem. But in any case, at this point, because of the lack of interaction with the outside world, school culture becomes recycled from generation to generation. So definition becomes something you scorn at. It's just, why do you want to bother with it? You think about it. In your normal transactions in the classroom, under normal circumstances, when do you ever need a definition? Can someone give me an example of when you normally teach your classes, there was really some critical definitions you had to insist that your students know? Did it happen? Yeah, okay.
Yeah, no, my students always mix up the integers and whole number.
That is just not, okay. Yes, that in other words, they got the name confused.
Yeah.
That's not what I had in mind. I mean, the concept fairly complicated, and you insist that they know the fine distinction. For example, what does it mean to say one number is less than another? Do you ever worry about it? Not about, you're right, I did not phrase my question correctly, and I don't think there's any way I can phrase it correctly. In some sense, what you said is correct. The definition of the whole number is something, and the definition of integer is something else. Yes, but I have in mind something a little bit more sophisticated than that. It's not just a name, but a complicated concept in which detailed information is available, and that detailed information makes the whole difference, like this. Less than. Now that's not obvious, right? So to make sense of this, you have to know the whole process of counting. And then you say, this is less than that. If you can count from this point, from this number, many steps or several steps to get to this number. Right? That's what I mean. It is a cognitively complex statement. Now, it almost never happens in school mathematics. In the textbook. No textbook I know of ever makes use of definitions. Yeah.
Well, they do give you definitions, but the problem is that they're either incorrect or incomplete.
And never used. That's even more important.
Yeah.
And never used. Yes, they give definition. Oh, well, next time I'll bring some transparency to show you. They define everything. You should. Some of them are true. I'll show you. You must have come across them. Maybe you didn't know it. I mean, I'm sure when I show you, you say, "Oh, yes, I've seen it before." They're funny. They're absolutely funny. Some of the definitions given. But it doesn't matter. You see. So long as you never make use of definitions, what does it matter what you say? See? But to us, so the minute you're here, anything you say, you're accountable for, and I'm going to catch you. Right? Why is that? Because if you start practicing this, then you begin to gain their trust in you. You say something, and they ignore you, of course. And then at some point you ask them, what is that? Why did you do this? And of course they don't remember. Then you say, remember I told you. You remember? Now, after the first 2-3 times talk, it makes no difference. But after 6, 7 times, they begin to say, we better listen to our teacher because otherwise she's going to catch me. And then once they, what does it mean? It means that they start to listen to you. And the instruction you give out, they begin to keep in mind, begin to believe you. And that's what learning is about. That's what learning is about. What you say matters to them, they digest it and try to use it. That's learning. I mean, that's teaching, sorry. That's teaching. Right? And you want to be good teachers. And that's what we're here for. You want to go back and be good teachers. You cannot be a good teacher if they don't listen to you. I want you to gain that trust first. That's the first step. So I say all that because at this point, now we do things that are actually obvious to you. The only difference is that I'm not going to give you precise explanations. And I hope that you think about it and say, that makes sense. All right, now look at this. With this minute, right? So now suppose I have two integers. Let's say m less than n. I'll take another whole number. What did I say? Integer or whole number? Oh, two whole numbers, n and n. Right? And a is also a is not good. Okay. So n less than n, not equal to 0. None of them 0. I want to say that then k then km less than kn. You believe that, of course. Right? Because if this is true, right? 3 times 137 less than 3 times 181. So that's obvious. One way to see this is the following, right? Roughly, if you think of line segments, 137 is this long. Right? 187 is longer, right? 181 is longer. You string 3 of them together. Well, you string 3 of these together. If each one is longer than the one above, of course, why not, right? The 3 of them together is longer. You believe it. That's good, but not very good because it doesn't quite give you. It's just a little bit sticky. So that's a better way to see this in one stroke. And you do that now. Now that I'm asking for it, can anyone think of a reason to see why this? You can explain this a little more clearly, more insightfully, more snappily. You think of that? What is an interpretation of multiplication? Yeah, what else? Area. What does it say? Now that I said, what is this? A rectangle, eh? Now you see? You have two rectangles, right? This is K. You have this M. This is M. Yes? What's Km? That's Km, right? What's Kn? The larger rectangle, yes. That. Difficult to show. The red rectangle is Kn. Well, I hope you agree this is, somehow, I cannot tell you why I think it's better, but if you don't agree, it's fine. Because the reason you have this image in mind, what? No, right away you see, this is a bigger rectangle, and so that was bigger, right? Contains more things there. It conveys that feeling of bigger right away. Instead of this grubby comparison, one by one, put them together, all complicated. Is that good? Now, of course, there's the same statement for addition too. That Kn equals N. Then K plus N. But that's easy. That's much easier, right? Use segments and you see right away. But this is something that you need to use. Alright? Is this good? Now, there's another reason, by the way. There's another reason of why I introduced this. Yeah, sometimes I never get around to saying this. The segment by segment thing is good for whole numbers because it is. The whole number times a number, it's repeated addition, therefore you are putting so many segments of the same length together. Yes, that's good for whole number. But it won't work for fractions, right? We talked about it already. You multiply fractions, you cannot talk about. You add 1/5 of a segment to itself, and there's no such thing. When that happens, you see, for all other numbers, other than whole numbers, that's about the only way you can think about multiplication. And when we come to fractions, which happens next week, for exactly the same argument. In other words, this statement, what now says up here says K and N are all numbers. If I change this to fractions, everything continues to be true, but much more than that. The whole reasoning here continues to be true. So in other words, you learn one thing, you get 3 or 4 things for the price of 1. So you want to learn and you want to teach things like that. Very big becomes worth learning, right? It's a sort of a, what is it? I mean, yeah, several things for the price of 1. You learn one thing and then useful for many times. So that's the reason. Now, But that's this first thing I want to review about comparison. The second thing I want to review about comparison is also very obvious, but it has a fancy name. So that's peculiarly mathematics. Trichotomy law. You know Latin, right? Tri means three. So it means cotomy means cotomy means division. Now the only three possibilities. So given any two numbers, whole number. And one and only one of the following three possibilities occurs. And of course, could be equal to n, and of course could be less than n, and m could be bigger than n. So this is what accounts for the name trichotomy. There are three things, three divisions. Division into three things. Now this is the most boring statement possible, right? I mean, if two numbers, they're equal or they're not equal. How is that for being done? But in mathematics, it's actually important. Now, you will not appreciate the importance unless you do a little bit more. Other kinds of, no, you do school mathematics, you come across situations where you cannot say something like this. You all have some algebra. I give you two polynomials. What are you going to say about two polynomials? Can you say, between two polynomials, one and only one of three things happens? One polynomial is equal to the other. One polynomial is bigger than the other. One polynomial is smaller than the other. Can you say that? So only when you fixate on numbers, or this is a dumb statement to make. But the dumb statement is made because in the broader context of more things that you think about, then you say, oh, we thought we took it for granted. Should have. Doesn't happen often. In fact, it almost never happens. Except among these things. You all remember something about complex numbers?
About what?
Complex numbers. You don't remember the name, right? So, find something that you remember. Let's see. Oh yeah, I'll give you two triangles. What did you say? Given two triangles, one and only one, three things occur. They're equal. One is bigger than the other, one is smaller than the other. Does it make sense to you? Of course not. See? So you look around and say, oh yeah, well this of course. This is why real numbers, what we call fractions, whole numbers, negative numbers, irrational numbers, all come together. That's why no matter what you do, so long as there's human civilization, that is always the starting point, precisely because of trichotomy law. That's where everything is possible. Given two things I can compare. So we single it out because we're going to say the same thing when we come to fractions. Given two fractions, well, only one or three things occur. And of course, as I keep saying, this instance, we're never going to do something that is to say, well, it's so pretty, look at it. It's always because it's useful. And you see how it's used in the code, right? And I forget, someone will remind me. Anyway, so I just want to say, now 4. Why it's true? Does anyone worry about why it's true? You know why it's true, right? No, why it's true?
Because of the number line?
Yeah, for the number line, what can it be? Either the two ones coincide, one to the level of the other, right? So that's very good. That's exactly why the number line is important, by the way. So that's the number line. Every time you're here, you're home. There you recognize things. And you have fancy systems, and then you lose so much information, and you find ways to replace it by a number line if possible, and so on. That's what happens. Given any other kind of thing, given a polynomial, for example, then you find ways to reduce the polynomial to a number line. So, remember this. So I'm done with this part. Review anyway. Nobody has ever finished with that comparison. Why the comparison? Now, in school mathematics, now it's a little better, but it used to be, when I was a student, we used to get the idea that only when two things are equal, that's important. Because in all computations, right, 1 plus 5 equal to 6, 22 times 2 equal to 44, it's always equal, right? So we got the impression that, well, it's equality that's important. But it's completely false. In everyday life, the only thing that's important is comparison. One less than the other. When do you ever get equality? Look up, all of you here. Do you think you're going to have equal heights here? I doubt it. That's always one bigger than the other. Take your weight. You're going to have equal weight here? No. In real life, so there's some improvement over the years, at least in this respect, that nowadays there's a more serious attention given to inequality. And that's what it's about. Comparison is what it's all about. Inequality. So keep this in mind when you teach that. Sometimes just remember to also tell your students that you have to know how to decide whether one thing is smaller than the other. Okay?